Welcome back to Power Electronic Labs. Today we're going to look at Lab 3, Power Components. We're going to look at the purpose of this lab, the circuit and principle, and then we're going to build the prototype and test results. Let's take a look at the purpose. The purpose of this lab is to test the switching conditions of the power components. The four power components being tested are SCR or thyristor, triac, MOSFET, and IGBT. To determine the switching conditions, we're going to test the following: power polarities, positive or reverse, gate signal, high or low, and switching states of the power component, on or off. Now we're going to take a look at the circuit and principle. Here's the schematic of the prototype circuit. On the left, we can see a common power path, including an external 12-volt DC and an LED light, which we're going to use to test each individual power component: SCR, triac, MOSFET, and IGBT. To arrange for the power polarity, we would connect the two pins found on your common power path, P3 and N, accordingly. For example, for the positive power polarity of SCR, you would connect P3 to A and N to K. For the reverse polarity, or the negative polarity, we would connect P3 to K and N to A. You can use a similar arrangement for triac, MOSFET, and IGBT. We're going to use two gate signals, GP1 for SCR and triac, and GP2 for MOSFET and IGBT as the gate signals. We're going to have a common gate input signal, GS, as the gate switch. To turn on the gate, connect GS to 15 volts, which is the output of the linear power supply in Lab 2. To turn off the gate, disconnect GS from 15 volts. The switching state of the power component will be indicated by the light of LED 3 found on your common power path. Now we're going to look into building our prototype. The components used in this lab are the PCB, printed circuit board, your linear power supply from Lab 2, a terminal, an LED, 5 resistors, one 15 ohms, two 510 ohms, and two 5.1K. And then you have the four power components, as shown on the right: an SCR, a triac, an IGBT, and a MOSFET. Now let's populate the components onto the PCB step by step. First, solder the 5 surface mount resistors, then the connecting pins. For the power path, P3 and N. For the SCR, G, SCR, A, and K. For the triac, G triac, T2 and T1. For the IGBT, G IGBT, C and E. For the MOSFET, G FET, D and S. For the gate signals, GP1 and GP2. Then solder a gate switch between GS and 15 volts. Now for the remaining parts, your terminal, and then your LED, and then the 4 power components, SCR, TRIAC, IGBT, then MOSFET. After soldering on all the components, we complete the building process. Now that we've built our prototype, let's test our prototype for results. Now, we're going to test the 4 power components one at a time. Here's the general procedure for testing one individual power component. Before powering up, you need to connect the power path according to the polarity and the gate signal to the specific power component you're currently testing. Then, plug in the transformer for the linear power supply we built back in Lab 2 to get the 15 volts for the gate switch. From an external DC power supply, add 12 volts to the terminal of the Lab 3 prototype. Then, push down the gate switch and release it. Then check the LED light, which indicates the switching state of the power component currently testing. This following clip shows the testing procedure. SCR experiments. For the positive polarity, connect P3 to A, connect N to K. When the gate signal is off, the SCR is off, the LED is off. Turn on the gate, the SCR turns on, the LED lights up. Turn off the gate again, the SCR remains on, and SCR cannot be turned off by the gate signal. For the negative polarity, connect P3 to K, N to A. At the negative polarity, the SCR does not turn on no matter the gate signal. In summary, to turn on an SCR, the polarity must be positive and a gate signal is needed. To turn off an SCR, the current needs to drop down to 0 or apply a reverse polarity. TRIAC experiments. For the positive polarity, connect P3 to T2, connect N to T1. When the gate signal is off, the TRIAC is off, the LED is off. Turn on the gate, the TRIAC turns on, the LED lights up. Turn off the gate again, the TRIAC remains on. A TRIAC cannot be turned off by the gate signal. For the negative polarity, connect P3 to T1, N to T2. When the gate signal is off, the TRIAC is off, the LED is off. Turn on the gate, the TRIAC turns on, the LED lights up. Turn off the gate again, the TRIAC remains on. A TRIAC can be turned on at both positive and reverse polarity. In summary, a TRIAC can be turned on by a gate signal at both positive and reverse polarity. To turn off a TRIAC, the current should drop down to 0. MOSFET experiments. For the positive polarity, connect P3 to D, connect N to S. When the signal is off, the MOSFET is off, the LED is off. Turn on the gate, the MOSFET turns on, the LED lights up. Turn off the gate again, the MOSFET turns off, the LED turns off. A MOSFET can be turned on and off by the gate signal. For the negative polarity, connect P3 to S, connect N to D. At the negative polarity, the body diode turns on. That is why the LED lights up all the time. In summary, at positive polarity, a MOSFET can be turned on and off by a gate signal. At negative polarity, the body diode turns on. IGBT experiments. For the positive polarity, connect P3 to C, connect N to E. When the gate signal is off, the IGBT is off, the LED is off. Turn on the gate, the IGBT turns on, the LED lights up. Turn off the gate again, the IGBT turns off, the LED turns off. An IGBT can be turned on and off by the gate signal. For the negative polarity, connect P3 to E, connect N to C. At the negative polarity, the body diode turns on. That is why the LED lights up all the time. In summary, at positive polarity, an IGBT can be turned on and turned off by a gate signal. At negative polarity, the body diode turns on. And with that, we're done our lab. Thanks for watching.